Today we are going to learn an iterative method used to solve linear system of equations. You know that if you have a linear system of equations, say a1x plus a2x plus a3x etc. equal to some value, and if you have such a number of equations where you have a number of unknowns, say x1, x2, x3, etc., you may solve it analytically. But then if you have a number of such equations and if you have a number of such unknowns, then solving it analytically may be quite difficult. So one of the methods to solve such system of equations are using iterative methods. That is an indirect method wherein you start from an approximation to the true solution and then derive at closer and closer approximations, and finally after a cycle of computations then you will get the solution of required accuracy. So it means that in a direct method the amount of computation may be fixed, but then in iterative method you cannot fix the amount of computation. It depends upon the accuracy you require. Okay, so now we are going to understand one such method, indirect method, iterative method used to solve linear system of equations. Okay, and this method is called as Gauss-Seidel method. Gauss-Seidel method. Okay, so to understand this method, first let me write a system of equations as a11 x1 plus a12 second coefficient and next second unknown x2. It goes on a13 x3 and final a1 n x n. Let this be equal to the coefficient b1. Similarly, you have a21 next equation x1 plus a22 x2 a23 x3 plus a2n xn b2. Okay, there are several equations. Will the last equation be an1 x1 plus an2 x2 plus an3 x3 plus an n xn equal to bn. So these are the system of equations we have. So here, in order to do this, all the diagonal elements a11, a22, a23, a33, like that, all the an3, ann, right? All the diagonal elements should not vanish. Okay. Then if at all it gets vanished, then the system of equations should be rearranged so that that condition should be satisfied. That is, all the diagonal elements of the system of equations should not vanish. Okay, if that is the case, now I'm going to write this equation or modify this equation in such a way that from the first equation I'm going to write an equation for x1. From the second equation I'm going to write the equation for x2, like that. Okay, so that is, you will just see what I'm going to do. From the first equation I'm going to write an expression for x1. So I'll keep this x1, a11 x1 here and bring all the other to the right side and then divide everything by a11. So I will get the value for x1. So that is, I can write x1 equal to, okay, the first one is b1 divided by a11. I divide b1 by a11, then I'll take all the other thing to the right hand side, and that also will be divided by a11. So minus, when you do, you will understand a12 divided by a11 x2. Okay, this goes on, and the final value will be minus a1n, last term, divided by a11, then xn. Similarly, I am going to write the xnth value. Xn is equal to bn divided by x1. When you write, I am going to find the formula for xn. Okay, so that means all the other terms will be taken to the right hand side, and that will be divided by ann. So I am writing it for xn. Okay, so that means that will be ann minus an1 ann x1 minus an2 by ann x2. Okay, Gauss. Final term is n is here, right? That is, I'm writing the equation for xn. So the previous term, till the previous term I have to take to the right hand side. So the last term will be what? That will be an minus 1, right? An minus 1 divided by ann, then xn minus 1. Okay, so that is I've written the expression for x1 and x2. Now let me suppose the first approximation. You have written the equations for x1, x2, x3 like that, etc. up to xn. So when you find that x1, the first approximation, suppose the first approximation is x1. Let me call them as x11. The first approximation for this x1, let me call as x11. Okay. Similarly, the first approximation for x2 is x2. First approximation for x3, let it be this one. So like that, I have the first approximation for xn. So let these are all unknowns. x1, x2, x3, etc. up to xn are unknowns. So let me call the first approximation to these unknowns as x11, x21, like that, etc. up to xn1. So this first approximation, let me substitute to the right hand sides of the equations, previous equation written. That is, you know that you have this x1, x2, etc. In that way you are finding out new x1. That is, with the x2, x3 first approximation, you find the value for x1. Then when you write the value for x2, the first approximations for the other values, you can find the value for x2's next approximation, like that. Okay, so then did you understand? That is, I can write the first approximate value for x2. So I can write x21, then I can write for x31, then in that way xn1. Then with these values I find the next value for x1, next approximate value. So I will write x1 as x12. That is, with this first set of approximation, I am finding the second approximate value for x1. Similarly, I will find the second approximate value for x2 using the first approximate values for x1 and rest of the other terms. I'll show you. That is x1 second approximate value, and that is equal to, this is from the previous equations only. Minus a12 by a11 x2 1. The first approximate value, a1n divided by a11 xn, first approximate value. Then I'll use all the first approximate value to find the second approximate value for x2. That is the second equation. Likewise, you can find for second approximate value for the xn as bn by a nn minus an1 by ann x1 first approximate minus an n minus 1 x n minus 1 first approximation. And then so with this first approximate values, find all the second set of approximate values. Similarly, with the second set of approximate value, you can find out the third set of approximate values, right? You can go on continuing until you get the approximate value according to your needed accuracy. Now, now let me call if x1n is the nth approximate value. N is the nth approximate value, xn n. Then you can find the xn plus 1th approximate value using the same relation. Xn plus 1 will be equal to b1 divided by a11 minus a12 divided by a11 x2n. Then all the terms minus a1n divided by a11 xn n plus 1. So all the n plus 1th approximate term can be found using the xnth term. So the whole thing can be written in the matrix form as x. The whole set of equations can be written in this column matrix, then all the other matrix. I can write this in terms of matrix as x is equal to b x plus c. So this is the constant term, that is c. B is the matrix constituted by a12 divided by a11. All the last term is a11 divided by a11. That is the last term in the first row. Similarly, you can have all the set of coefficients constituting the matrix B. And then the iteration formula, in iteratively you can write xn plus 1, right, is equal to bx n, right, that is the approximate, plus c. Okay, so this method, so with the first approximate values, you can find the next approximate values as you go on finding the next and next approximate values. So this method is actually called as method of simultaneous displacement. Simultaneous displacement, in the sense that simultaneously you go on displacing. First you all find all the second approximate values, then using this second set of approximate values you find the third set of approximate values for each unknown. Similarly, you simultaneously you go displacing each one. So this convergence method, and this method is known as Jacobi method. So this method is known as the Jacobi method of simultaneous displacement used to find the solve a linear system of equation. Okay, so we are going to discuss more about the Gauss-Seidel method, which is a more easier or more simplified method where you can get the solution convergent little more easily. So here what we are going to do in this case is, here we understood that we in the first term we put all the approximate values for x2 and then found out the x12. Then and then you found out again the x22, similar in that way you went on, right? But then there is one more easier way. In each step you actually find the second approximate value, that is using the first set of approximate values for x21, x31, etc. xn, you find the second approximate value for x1. Then in the next step, basically you can use this second approximate value for x1. That would be more better because it will converge easily, right? That is, here you have already found the second approximate value for x1. Then you can use this second approximate value here, and then all the rest of the thing you have only the first approximate value. Then you can find out the second approximate value for x2. Then in the next equation you can use the second approximate value for x1 as well as the second approximate value for x2, and then all the rest of the things we have only the first approximate value. Then you find out the second approximate value for x3, right? For in the next step you can use the second approximate value for x1, x2 and x3, and all the others the previous first approximate terms. Okay, so in this manner we can complete the first stage of iteration in the entire process itself, in the entire process, and it is repeated till you get the final approximate value for the last one. Okay, so did you understand that? So in this method you use an improved component as soon as it is available. That is, as soon as this second approximate value is available, you put it in the next equation. In the previous case you understood we were very slow, that is using all the first approximate values we find all the second set of approximate values, then using the second set of approximate values in these equations you find the third set of approximate values, like that. But here in that was actually Jacobi method, but then Gauss-Seidel method it is a little more faster converging method. So whenever you get a new approximate value, you plug in that in the next equation to find the next approximate value. Okay, so in that way it may converge more easily. For so if I can write, but then it needs a particular what do you say, a condition to be satisfied by the linear set of equations. So what I will write is I'll write that is in the Gauss-Seidel method, to make it more clear, it uses the improved component. Improved component means the new approximate value every time. It uses the improved component as soon as it is available. So whenever you find a new one, you plug that into the next equation, and hence it is called as method of successive displacement. The other one is simultaneous displacement. This is method of successive displacement. Hope you can understand its relevance, because successively in each term the newer and newer in each equation the new terms are being plugged in. So successively the new terms are replaced by the new ones. So that is known as a successive displacement method. Then obviously in the Gauss-Seidel method will be a more converging method. Easier it will converge. That is, you can understand, because as soon as you find a new approximate value, you plug in and then you find the next approximate value, right? So actually Gauss-Seidel method converges twice as fast as this Jacobi method. But then there is a condition that if you find with the system of equations given, then you can actually find whether this set of equations will get converged in the Gauss-Seidel method. So there is a method to find out that you know that you have a system of equations that, right, the sum of the absolute values of the coefficients, you know that in the system of equations you have a set of coefficients in each term, right? The absolute values of the coefficients should be almost equal to 1. Sum of the absolute values of the coefficient should be equal to 1, or in at least one equation the sum of the coefficient should be less than 1. That is, I can write it as, so all the coefficients means this one, a21, a22, sorry, not this one, I think, yeah, in this one, all these are the coefficients, b11 divided by a1, b22 divided by b2, a22. So all the coefficients, when you add together, all the coefficients should add together to be equal to 1, or it is said that at least in one equation, suppose I have 4 such equations, at least in one equation all the coefficients when added together should be less than 1. So then I can write it as the condition as sigma aij, all the absolute values when added together, divided by aii, the absolute value of that summed over j equal to 1, where j does not become equal to I. So it should be summed from 1 to n, and then all these added together should be less than or equal to 1. And I is equal to 1, 2, 3, etc. up to n. Okay, so this is the coefficient which you see. These are the coefficients sigma. I can say ai, all this together added together, that is aij, that is added together, all the coefficients means aij divided by aij divided by aii. So then summation of all these things together, and that should be less than or equal to 1, at least in one condition. Okay, this condition should be satisfied at least in one equation which is given. Then which is given, we will have a set of equations, then you will modify the set of equations in terms of x1, x2, x3 like that, and then in that equations all the coefficients added together, if at least in one of the equation given, if the coefficients is added together gives a value less than or equal to 1, then you can proceed with the Gauss-Seidel method of convergent method to solve the linear system of equations. So this is about the Gauss-Seidel method used to solve the linear system of equation. Now you can with the help of an example you can understand it more clearly. Okay, thank you very much.